We present our method Deformable Manipulation from Demonstrations or DMfD to solve robotic manipulation tasks on deformable objects. Many everyday tasks use deformable manipulation, such as folding clothes or cooking. The problem is hard due to the difficulty of obtaining object states and predicting their dynamics, especially since environment interaction can change these properties. Furthermore, their complex dynamics and high-dimensional configuration space can increase task difficulty. Analytical techniques succeed in certain conditions but fail to generalize with such tasks. We propose a new method, Deformable Manipulation from Demonstrations, or DMfD, for an agent to use experts' data while learning to solve deformable manipulation tasks. It is designed to work with state and image-based observations, with 1D and 2D deformables, and with simulation and real-world scenarios. Let us now look at the DMfD training pipeline. The agent obtains observations from the environment during experience collection or the replay buffer during training. Pre-populated expert demonstrations are denoted in green. For state-based environments, the observation is encoded by an encoder network. This state is then passed to the actor and critic, denoted by the blue and black arrows. Note that the observation for the actor and critic is the same as a state observation. Our method additionally can use image-based observations denoted by red. Here we see that image observations are cropped and encoded by a convolutional neural network with dense neuron layers. This image encoding is then passed to the actor and the critic, denoted by the red arrows. However, for image-based environments, the critic is privileged because it also receives a state encoding while the actor does not. Specifically, our method uses expert demonstrations in three ways. 1. We pre-populate the replay buffer with expert trajectories before training. 2. We leverage an advantage-weighted loss formulation, encouraging the agent to match with expert actions the replay buffer. Note that we balance this with an exploration term as well. And 3. We employ reference state initialization probabilistically, resetting the agent to a state along an expert trajectory. Then we compare the state trajectories of the expert and the agent for an limitation report. Our paper has 4 main contributions. First, to encourage wide exploration, we add an exploration term to the advantage-weighted loss. To deploy our method in real-world settings, we extend this advantage-weighted formulation to the image domain using CNNs and data augmentation. Second, we introduce probabilistic reference state initialization or RSI during experience collection. Instead of always resetting the agent to states seen by the expert, we invoke RSI probabilistically to promote exploration and learning in states that are difficult to reach. Third, we create 2 new simulation environments for cloth folding with 1 robot arm. We deploy DMfD on a real robot with minimal sim-to-real gap, indicating that it can work in real-world settings. Finally, DMfD outperforms LFD and non-LFD baselines on both state and image-based environments. Next, we discuss the results of the image-based environments. For the straightened rope task, we see that DMfD beats the best baseline with image-based observations. In this rollout, our method solves the task with 1 clean motion, whereas the best baseline still contains a loop. In the cloth fold image task, an agent must fold a flattened cloth along an edge. We see that our method beats the best baseline by folding the cloth with almost complete coverage of the 2 halves. Our new environments require the agent to fold a square cloth along a diagonal with only 1 end effector. In the pinned corner version, we successfully fold the cloth almost completely over itself, whereas the best baseline struggles with this task. In the unpinned corner version, we have similar success. Although the best baseline has improved performance, it struggles to complete the final motion. Here we present a real-world experiment on the cloth fold diagonal unpinned task on a variation with large rotation of the cloth. Our method is robust to variations in the real world, as can be seen in these rollouts for different cloth variations. Note that we have a sim-to-real gap of about 6%. In conclusion, our method works on state and image observations and is able to outperform LFD and non-LFD baselines. It is primarily because of the ways in which we use expert data and the balance with exploration. Additionally, we introduced 2 challenging cloth folding environments and deploy our system on a real robot. Thank you.